Good afternoon, and welcome to our final lecture in our Carnegie Observatory Spring Astronomy Lecture Series. I'm John Mulcahy. I'm the director of the Carnegie Observatories, and I'm also the science deputy for the Carnegie Institution for Science. Once again, we're coming to you live from the Huntington without an audience, hopefully for the last time, but we do appreciate you all watching at home. Before we get started, I'd like to thank our friends at the Huntington for hosting us again, and to acknowledge the Norris Foundation for their continued support of this series. Today's lecture will be given by Drew Newman. Drew did his PhD work at Caltech before coming to Carnegie as a Carnegie Princeton Fellow. After that, he was hired onto our staff, which is his current position. And Drew is an expert on kind of the high redshift universe, early galaxies and how galaxies change and evolve. And that's the topic we're going to hear about today. So without further ado, let me introduce to our stage Drew Newman. Drew.
Thanks, John, and thank you all for joining us this afternoon. What I'd like to do today is tell you a little story about how galaxies came to look the way that they do. In other words, how they get their shapes and their colors. These are questions that have occupied astronomers for about a century now. And so today what I'd like to do is just to tell you a little bit about the history of that question and some of the contributions that I and other folks at Carnegie have made over the years. And along the way, we'll take a little detour, and we'll see that, like in this image, sometimes the universe smiles on you a little, and you get the chance to look inside of very distant galaxies and see things that normally would be impossible. So just to begin, I love to look at beautiful images of galaxies like this one from the Hubble Space Telescope. And you don't have to look at very many of these. Even in this individual image, you can already see how different galaxies look. There's a huge range. Some of them are blue, some are red. You can see some that have spiral arms wrapping around their center, and others that look completely different, like the one at the bottom here that's a round ball of stars, basically. And the origin of that huge diversity of galaxies' shapes has occupied astronomers basically since the existence of other galaxies was discovered. You may have heard of Edwin Hubble. He was a Carnegie astronomer, very famous for two discoveries that really changed our view of the universe. The first was that the universe itself is expanding over time. And the second is that the fuzzy nebulae, as they were known, these fuzzy objects in the sky, were in fact each island universes that are entirely separate from our own Milky Way galaxy and located at incredible distances. So after Hubble discovered the existence of other galaxies, he was also interested in categorizing their shapes. And you can see that in this diagram from his book called The Realm of the Nebulae from 1936, where he separated on the left side the nebulae with elliptical shapes, and on the right side, those that have some spiral arms wrapping around their center. Now, over the years, since astronomers love classifying things, this so-called tuning fork has become elaborated and complicated. Here's a particularly stunning example from a few decades later. But nonetheless, that basic division that Hubble introduced has remained the cornerstone. So on the one hand, we have spiral galaxies, like our own Milky Way. These really catch the eye because you can see these beautiful spiral arms of gas and stars wrapping around the center. But maybe the more fundamental thing about those galaxies is their shape. They're thin disks of gas and stars. And you can see that really clearly when we catch an example where from the Earth we see it right on its edge, like this example here. You can also see in these images that spiral galaxies emit some blue light. And just as blue is the hottest color in a flame, blue light is emitted by the hottest stars, and those stars live short lives. So when we see blue light coming from a galaxy, that tells us it's a place where new stars are still being born. And when we see only red light, that's telling us that we're only seeing old stars, and stars are no longer being born. Other galaxies look completely different from the spirals. So on the right here, you can see a beautiful example of an elliptical galaxy. This isn't shaped like a disk at all. It's more like a round ball of stars. You can see another one in the bottom left here, and on the top left, you can see an example of an intermediate shape of galaxy, which is called a lenticular galaxy. These galaxies have a disk-like shape similar to the spiral galaxies, but it's kind of puffier and thicker, and they don't have the spiral arms. Now, you might have already noticed something, a pattern here, that the early extragalactic astronomers noticed. And that's that the appearance of galaxies, the different properties that they manifest, it doesn't seem to vary randomly or independently. They seem to be related to one another. So for instance, in the spiral galaxies, we see blue light coming from young stars, while in ellipticals, we have a red appearance because there are only old stars. Spiral galaxies contain a lot of gas that's fueling the birth of those young stars. Ellipticals, on the other hand, don't have any gas almost at all. And finally, spiral galaxies have their shape, that flat disky shape, because they're spinning. Stars and gas are orbiting the centers of the galaxy and producing this flat shape, whereas elliptical galaxies, on the other hand, are spinning little or not at all. So to put it another way, you can imagine categorizing galaxies according to these two fundamental properties that they have, their shapes and their colors. And in this diagram, you can see the spirals on the left, the ellipticals on the right, and red galaxies with little or no star formation happening are on the top, while blue galaxies are on the bottom. And this kind of diagram has a very important clue to how we think galaxies came to be. And that's that most galaxies today fall into one of the two big boxes that you see here. There are exceptions also, so there are blue ellipticals and there are red spirals, but those are much less common. So why is that important? Well, usually in science, when we're trying to piece together a story like how galaxies came to be, we look for the simplest explanation that fits all the facts. So when we see two attributes like color and shape that seem to go hand in hand, it's most natural to think that they probably have a common origin, a common cause. And that indeed has been the thought for how elliptical galaxies came to be, that they probably had some single major event in their past that both transformed their shape, making them round, and prevented them from forming more stars. So that must have been the most important event in the life of those galaxies. What kind of dramatic event could it have been? Well, the simplest idea, which goes back now many decades, is called the model of monolithic collapse. So in this picture, what we imagine is that there's a cloud of gas in the early universe, and over time that gas cloud is collapsing. And as it collapses, the gas becomes denser, and eventually it becomes dense enough that it ignites star formation, which burns through all the gas and leaves behind a ball of stars, which, the theory goes, could look like an elliptical galaxy. Now, in the modern theory of galaxy formation, we know that this idea of gas collapsing under gravity is absolutely pivotal. It's really how all galaxies formed. Although today we understand that it's the dark matter that provides most of that gravity. And if you were able to see Andrew Benson's talk earlier in the series, then you learned a lot about dark matter. But what's a lot less clear is whether this is really how elliptical galaxies came to be, whether they sort of emerged whole cloth from one giant collapse event. There's another idea, a different one, and it's based on the idea that galaxies don't live in isolation. They have neighbors, and they can collide with the neighboring galaxies and merge with them and form new galaxies. And in fact, our own Milky Way galaxy is currently on a collision course with its nearest large neighbor, the Andromeda galaxy. This is actually a galaxy you can see with your naked eye at a dark site. It looks like a little faint smudge, like I've highlighted here. And it's the very first object that was known outside of our Milky Way galaxy. This is a computer simulation of what we think is going to happen to the Milky Way and Andromeda over the next several billion years. So the simulation begins with a rendering of the Milky Way spinning around. Sorry, it looks like it's a little frozen here. And in a moment, you'll see the Milky Way, the image zoom out, and Andromeda will appear in the lower right. Now, currently, the Milky Way and Andromeda are approaching each other slowly, but on essentially a head-on collision course. And so what that means is that in about 4 billion years, the galaxies will approach each other closely, as you see here, and they'll pass by one another, and their stars will be flung in all these different directions. As you can see, the galaxies will slow down and begin to reapproach. And this time, they will actually merge and coalesce and form a new galaxy. And even better, what this simulation shows is that galaxy could look like an elliptical galaxy. So 2 disk galaxies became an elliptical. Now, by this point, the sun will have evolved enough that it's not really clear the Earth is going to be habitable anymore, so we probably won't have any descendants around to witness this, but it's a shame because the sky is going to look absolutely amazing. So this is a different visualization that shows how our sky will change as Andromeda approaches the Milky Way. You can see it getting larger and larger, then the merger happens, and it progresses, and at the end, we have the appearance of this new elliptical galaxy. And our night sky will just be totally dominated by the center of that galaxy. It'll be just ablaze in red light like you see here. It's really incredible. Now, this key idea that disk galaxies could collide and change their shapes into elliptical galaxies, this was investigated by Francois Schweitzer, who was an emeritus astronomer at the Observatories. And he wrote a very famous and influential paper where he showed that the galaxy that's emerging from the collision that you see in this photograph, in fact, does resemble a newborn elliptical galaxy in how its stars are distributed. And by now, the Hubble and other telescopes have recorded many beautiful images of galaxies colliding and in different stages of merging and coalescing. And we know that this is an important way, probably the most important way, that galaxies change their shapes and are still changing their shapes today. Now, when I arrived at Carnegie as a postdoc, I became interested in whether this story was different long ago, early in the universe's history, in the first few billion years. And a great place to look for that is in the most massive galaxies that have hundreds of billions of stars, like the example you see here. These galaxies today are almost always ellipticals, and their stars are truly ancient, about 10 billion years old. So we know that whatever formed these kind of monster elliptical galaxies was in the very distant past. The images we were just looking at of emerging galaxies, those are practically in our cosmic backyard, relatively speaking. And what I wanted to know was whether these giant galaxies were made in the same way. Was there some dramatic event, like a collision of galaxies, that ended their ability to form stars and transformed them into these round balls that we see today? Now, in astronomy, of course, we can't run an experiment. We can't control the fate of galaxies. So instead, we just have to think of some observations of the universe that can test a hypothesis. And in this case, I thought of 3 steps for the experiment. The first would be to find massive galaxies in the distant past, galaxies that could be ancestors of the one that you see here. The second would be to find those that seem to have already finished forming their stars early in the history of the universe, so that today stars would exclusively be old, just like the example you see here. And then finally, once we found those, we could compare their shapes to elliptical galaxies today and see whether they had already transformed, or maybe something different had happened. Maybe they were only partly transformed. Now, if it's true that these monster elliptical galaxies were made all at once, what would we expect to see if we looked into the far past? Well, if we could look about 10 billion years ago, then we might actually see that they looked rather similar to what they look like today. They might have just ended their star formation, formed all their stars, and attained this elliptical shape, all the hallmarks of an elliptical galaxy. Now, you might be wondering how we can actually look 10 billion years into the past to answer questions like this. And here, astronomers are really helped out by the fact that telescopes are really like time machines. So when we look at an object that's 10 billion light years away, we're seeing it as it was 10 billion years in the past. And that's just because of the amount of time that it's taken for the light to travel to us. Now, our look at these distant galaxies about 10 billion light years away got a lot sharper back in 2009. That's when the heroic Atlantis Space Shuttle crew performed the final servicing mission to the Hubble Space Telescope. And they installed a new camera called Wide Field Camera 3. And this camera is really special because it's sensitive to infrared light. Now, when a very distant galaxy emits visible light, the kind we see with our eyes, that gets stretched out as it traverses the universe that's expanding on its way to us on the Earth. And so it appears to us today as infrared light. And so since the Hubble, by flying above the Earth's atmosphere, can take incredibly sharp images, it being outfitted with these new infrared eyes really opened a new window into what early galaxies looked like. And in particular, we could start to look at proto-elliptical galaxies. I'm calling them proto-elliptical because we think these are some of the ancestors of the big elliptical galaxies we see today. And here is a collection of some of the images that Wide Field Camera 3 took after it was installed. And they might not look like much, little smudges, but actually each of them is a galaxy with about 100 billion stars whose light has been traveling to us for about 10 billion years. And even more than that, these are special because even though we're seeing them when the universe was only about 20% of its current age, these galaxies already seem to be done forming their stars. That's why they have this red color. So we think many of these are destined to become elliptical galaxies. And the question I was interested in is, are they already? Are they sort of fully formed and done a few billion years into the history of the universe? And when you look at these images from the Hubble, at a first glance, it kind of looks like it. I mean, we don't see obvious spiral arms. They look kind of featureless, kind of like an elliptical. But once you start to look at things more closely, that impression breaks down. So to demonstrate that, here I've ordered a lot of those images from Hubble of proto-elliptical galaxies according to how far away they are, and therefore how far back in time we're looking at them. And once you can compare galaxies across time, you immediately see something that's very striking, which is that those most distant proto-elliptical galaxies are very small. And I've put everything on the same scale here, so things don't look small simply because they're farther away. And this was really a big surprise, because some of the galaxies at the bottom here are so massive and yet so small that they don't really resemble any galaxies that are around in the universe anymore. It's almost like images of an extinct species. And when I was a graduate student, my advisor gave a presentation on what he thought were the most important questions concerning the evolution of galaxies at that time. And he thought understanding how these proto-ellipticals came to be and how they evolved into today's galaxies was one of the most important. So that's what really piqued my interest in this subject to begin with. Now, the reason that that was such an important discovery was that these galaxies had every right, I think, to be kind of the most boring galaxies in the universe. We could easily, as I've said, just looked back in time and more or less seen that they looked like they do today. They just formed very early. But instead, when we could see their sizes with Hubble, that told us something important, that they, in fact, were not formed all at once. We're seeing them 10 billion years ago, and they're only kind of partly transformed. They have red colors, like today's ellipticals, but they're not the same. And so that told us that we had to rethink what we thought about the lives of those galaxies. They must have been more complicated than we expected. And in particular, they must have found a way to keep growing over time, even after they had finished making new stars, which is the main way that most galaxies grow. So that was really interesting, and it got me wondering what else we might have gotten wrong about these galaxies. In particular, what are their shapes really like? And this is a surprisingly difficult question to answer, even for galaxies in the nearby universe where we can take beautiful images like this one. It's very hard to tell the three-dimensional shape of a galaxy just by looking at it. So, for instance, this galaxy, if you were to classify it as a spiral and an elliptical, you might say, yeah, it looks like an elliptical galaxy. And if you thought that, you'd be in very good company, because many professional galaxy morphologists that particularly specialized in classifying images of galaxies decades ago all classified this galaxy as an elliptical. But nowadays, we think the galaxy probably has a shape like the one on the right. It's just that we're seeing the one on the right along the edge, and on the left we're seeing that galaxy from a different angle right on its face. So why do we think that? The reason is that we've begun measuring not only the shapes of galaxies, but also measuring the motions of stars within those galaxies. And the telltale sign of a disky galaxy is that the stars are spinning around the center of the galaxy. They're rotating around the center. The galaxy as a whole is spinning, while an elliptical galaxy, remember, does not spin. So we've made that measurement for the galaxy on the left, and that's how we know that its shape is actually like a disk, not a round ball. Okay, so now you might be thinking, are those proto-elliptical galaxies that we've glimpsed with the Hubble, are they spinning or not? That's what we need to know to answer the question of their shapes. But unfortunately, when I was a postdoc, it seemed that we had hit a technological wall. There was no telescope, and there still is no telescope that can directly measure whether these kinds of galaxies are spinning. They're just too small, too faint, too far away. And so, one option would be to wait for the next generation of telescopes. And I'll tell you a little more later in the talk about the exciting new things we're going to have in the next decade. But the thing is that no astronomer really wants to wait for the answer. It takes a long time to build telescopes, and we're impatient. So I thought we needed to find a way to work around this problem. And the story of that workaround is very interesting. It starts around 300 years ago with a notion that Isaac Newton had, or at least that he might have had. Now, Newton wrote a famous treatise outlining his theory of optics. And at the end, he posed a series of rhetorical questions, which are called the queries. And you can see the first one of them here. Newton said, do not bodies act upon light at a distance and by their action bend its rays? And ever since, historians of science have been very intrigued by this notion because it seems to suggest that Newton thought that gravity could not only determine the paths of objects, but actually bend light rays. And if that's what he thought, I think this would be the first known mention of that idea in the historical record. Now, really, historians think that probably Newton was not referring to that in this quote. If you read all of the queries, it seems more likely he was referring to a different optical phenomenon called diffraction. But nonetheless, in the modern theory of gravity, the theory of relativity that Einstein developed, massive objects definitely do bend light rays. Now, if you were able to attend Tom Holowein's lecture, you saw a great demonstration of relativity. You can just see one little rendering here of the sun warping the space around it and the Earth orbiting it. And in Einstein's theory, because massive objects are warping space, what we see as a gravitational force is really just that object following a path in that curved space. So in this visualization, the Earth orbits the sun just as naturally as a ball rolls down a hill or a marble spins around a funnel. And in Einstein's theory, light rays definitely are deflected. Now, what Einstein realized was that this implied something pretty incredible, which is that a massive astronomical object, like a star, for example, could actually act similar to an optical lens. So how is that possible? Well, imagine a star emitting light in all directions, and some of that reaching a telescope on the Earth with an observer, as I've depicted on the left here. Now, what Einstein realized is that if we were to insert a massive body like a star directly between us and the more distant star, then the gravity of that intermediate star could actually bend the light rays emitted by the more distant one and focus them on the observer. And what we would then see on the Earth, because we have light arriving from different directions, would be two different images of that same star separated on the sky. It's an incredible prediction, and Einstein, of course, did the calculation and found that the separation between the stars would be so small that at the time it would be completely unobservable. And so in 1936, he said, of course, there is no hope of observing this phenomenon directly. Fortunately, though, in the very next year, his doubt was a bit called into question. So in that year, Fritz Zwicky, who is a sort of cantankerous genius who worked at Carnegie and Caltech, seemingly always depicted with this amazing photo. He was considering in that year the Coma cluster of galaxies. It's basically a place in space where there's a lot of galaxies packed into a small volume. And what Zwicky was measuring was the motions of those galaxies. And he realized that they were moving so quickly with respect to each other that they should have just flown apart a long time ago. And the only way he could understand that was if there were some large, unseen mass that was holding all the galaxies in this cluster together. And based on those measurements, he wrote, I think, one of the most prescient papers in the history of astronomy. He measured all that missing mass in several ways. He coined the modern term for it, which is dark matter. And he realized that if galaxy clusters actually had this huge reservoir of invisible mass, then they could act as a gravitational lens on a much bigger scale than what Einstein had considered. Einstein was just thinking of a single star bending the light, but here a galaxy cluster has hundreds of trillions of masses, of solar masses. And so it could potentially act as a gravitational lens on a much grander scale and lens not just single stars in the distance, but in fact distant galaxies located far behind the galaxy cluster. It's a really amazing and bold prediction, and in fact it stood for about 50 years. It wasn't until the 1980s that the first example of gravitational lensing by a galaxy cluster was found. And this is that first image. And it may be a little hard to see what we're looking for if you haven't seen this before, but I've highlighted in the oval here a very elongated, distorted image that we call an arc. It's actually much easier to see in a modern image from the Hubble Space Telescope. Now, in this image, all of the red galaxies you see reside in the galaxy cluster. And this giant arc that I've circled is an image of a galaxy located far behind the cluster. And as its light traverses the distance from the distant galaxy to us, and it passes through this cluster's immense gravity, the image gets extremely distorted and warped and magnified. It's a really amazing phenomenon, and it's a very important tool for astronomers too, because basically the cluster is acting like a natural telescope. It's sort of boosting the power of our man-made telescopes and letting us look inside this very distant galaxy in much greater detail than we would ever be able to do otherwise. And remember, because more distant galaxies we see as they were earlier in the universe, that means we're basically getting a clear look back in time. Now, this isn't the only galaxy, actually, that's being magnified in this image. Let me just show you a few more. There's actually a lot. I think the principle here is illustrated nicely in this animation from the European Space Agency. So here, we're imagining that there's some distant galaxy emitting light, and we imagine that we can insert a galaxy cluster between the Earth and that distant galaxy. And as the light from that galaxy makes its way toward the Earth, it takes this curved path, which results in us actually seeing two different images of that same galaxy on the sky. And this is now an image from the Hubble telescope where that's actually happening. So here we have two different images of the same galaxy. Now, when those images are brighter and closer together, they can merge and make these giant arcs like the one you see in the kind of 3 to 6 o'clock position here. Now we know many examples of gravitational lensing. I'm just showing you a few, and it's become an important tool for learning about dark matter and for learning about distant galaxies. And sometimes you get lucky and you discover one, like the one in the bottom right here, that look like something fun. This is the famous smiling lens. Okay, now you might be wondering how this relates to our problem with the proto-elliptical galaxies. Well, we want to know whether those galaxies are already ellipticals, and we're going to try to find that out by measuring whether they're spinning. And our main problem was that they're too small for us to see that, so some magnification by this gravitational lensing phenomenon could really help us out. So what would we need for that to happen? Well, what we'd have to find is a proto-elliptical galaxy that's located almost exactly behind a galaxy cluster as viewed from the Earth. And not just almost behind, it has to be very precise, within about 0.02 of a degree. So to give you some perspective, that's as though someone about a mile away is holding a candle, and someone a half mile away has $0.25, and they align it with the candle well enough to block your view of the flame. So that's pretty well aligned. And even though the universe is a really big place, galaxy clusters and proto-elliptical galaxies are both pretty uncommon. And what we would literally need to find is the case where the stars are aligned between these rare objects, or at least the dark matter and the stars are aligned. And so for that reason, when I was a postdoc, there had only been one case of this that had ever been discovered. And I was really interested in whether we could find more, whether it would even be possible. And so I started thinking about what it would take to hunt for proto-elliptical galaxies that have been gravitationally lensed and magnified. Now, the first thing that was pretty clear was that we needed some kind of strategy. You can't just start taking images of the sky at random, because you would have to be incredibly lucky to find what we're looking for that way. But the good thing is we know where a lot of galaxy clusters are, so we can start just by pointing our telescopes at those. Even then, though, you still have to be pretty lucky when you look at a galaxy cluster. I thought maybe 1 or 2% of the time we might find what I was looking for. But the good thing is that if you're patient and you have enough time and you can look at enough clusters, then it stops being a game of luck. You know you should eventually find something. It's just a question of how often, how long it's going to take. And since I had just come to Carnegie, which I knew was a place that encourages risky and long-term research, I thought it was worth taking a shot. And the really key part of this hunt is to look at these clusters in the right way. Astronomers usually take images of the sky through glass filters that isolate particular colors of light. And if you choose those glasses carefully, then the proto-elliptical galaxies that we're looking for are blindingly obvious. You'll see it in a minute. They just scream out of the image. So here's an example of that. This is a proto-elliptical galaxy 10 billion years ago, seen by the Hubble Space Telescope. In invisible light, you really don't see anything at all. As we move to infrared light, the galaxy starts to appear. And when we look at even redder infrared light, the galaxy is actually quite bright. So that's a very distinctive signature. And it's really what makes it possible to find the needle in the haystack, so to speak. And because the infrared sky is much less well explored than the sky in visible light, the kind we see with our eyes, I thought it was possible that there could be some really spectacular things waiting out there, just still waiting to be discovered. So I started this hunt looking for lensed proto-elliptical galaxies using Carnegie's Magellan telescopes, which we operate in the Atacama Desert of Chile. And the reason I was able to use these beautiful telescopes for this project was that Carnegie, and specifically Eric Persson, who is an emeritus astronomer, had built a really fabulous camera for making infrared images. It's called 4-star. And besides that, one of my colleagues, Dan Kelson, had written brilliant software that runs on a computer cluster down at the telescope, and that allowed me to process all these images that we were getting and to search for these lens proto-ellipticals literally on the same night that we had observed them. So this is what it was like to be at the telescope. We'd take a couple of images, little snapshots, move on to the next cluster, take a few snapshots, move on to the next. And meanwhile, the computer cluster is running and these images are starting to appear, and I'm looking for a proto-elliptical galaxy. And for a long time, nothing really stood out. In fact, to be honest, I was starting to get a little bit worried because my new colleagues had just given me all this telescope time and I thought I might not find anything. But I kept going for a while, and eventually I saw something like this. Let me blow it up. Here you can see when you choose the right colors, the galaxy really pops out. It's the yellow thing that you see here, the giant arc. It's clearer in a Hubble image that we got later. And this galaxy is really special. It turns out to be the brightest distant galaxy in near-infrared light that has ever been discovered. And it's so bright because it's a hugely massive proto-elliptical galaxy, and it's located almost directly behind the galaxy cluster that you see here, which is greatly magnifying it. So I was really happy with this. It really felt like kind of hitting the jackpot level of luck. And I wanted to find more, though, and so I started using not only Magellan, but the Hubble Space Telescope. And one of the great things about Hubble is that anyone can apply for time to take data with the Hubble, and anyone can download the data the Hubble has taken. So you can go to this website that I've put here and, for instance, download all of the images of galaxy clusters Hubble has ever taken. And that's basically what I did, and I started looking through all that data also. And in the end, after looking behind about 230 galaxy clusters, we found 5 lensed proto-ellipticals, just what I was looking for. And you can see them boxed in these 5 images. Now for 2 of these, the example in the middle and the one on the lower right, the lensing has created multiple images of the same proto-elliptical galaxy. So that's why you see the numbers 1, 2, 3, and 4. In the other 3 cases, we only get 1 image, but it's been greatly magnified and elongated. And that's really just what we need to be able to start looking inside of those galaxies now that they've been blown up by the lensing. Now, if you remember what started us down this road, it was the question of whether these very early galaxies had already transformed into ellipticals like we see today, or perhaps they look like something different. And remember, the key test was whether they are spinning or not. That would tell us whether they were disks or balls of stars. And now that we've discovered these lens galaxies, we can finally test that. Now, the way we tell if a galaxy is spinning or not is by recording its spectrum on two sides of the center. And what you see here is an example of a spectrum. It's basically the amount of light that the galaxy emits at very specific colors or wavelengths. And so what you see is the dips in this diagram are specific colors where the galaxy is darker. Now, if the galaxy is spinning, if you think about it, that means one of the sides of the galaxy will appear to be approaching us, and the other side of the galaxy will appear to be moving away from us. And the side that's approaching, the light emitted from that side will be blue shifted, and all those dips that you see in the plot will move to the left. And this is analogous to the Doppler shift that you know for a siren on an ambulance, for instance. It sounds higher pitched when the vehicle is moving closer to you and lower pitched as it moves farther away. And conversely, the other side of the galaxy, if it's spinning, will be receding away from us, and its light will be redshifted. And so the signal we're looking for is a movement in these dips where the galaxy is dark when we look in different parts of the galaxy. And in the very first case where we tried to do this, the lensed proto-elliptical galaxy that you see in the image on the left, that's exactly what we found. One side was blue shifted, one side was red shifted. It's the telltale sign that that galaxy is a spinning disk. And this was really exciting because it was the first time that we have ever been able to measure the motions of stars within such a distant galaxy. Now, as exciting as that was, I knew that you can never really tell too much from looking at one galaxy because galaxies live very diverse lives. But the amazing thing is, when we started to observe more of these lensed proto-ellipticals, they all showed the same thing. Spinning, 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 and spinning. What you're seeing here in these four plots is the velocity of stars as you move across each of these four images. So the red points that lie above the horizontal lines are where the galaxy has a positive velocity. That's where its stars are receding away from us. And in every case, what you see is that the left side has this redshift, and the right side, conversely, where the points are colored blue, is blue shifted. It's approaching us. So this was really exciting because we have only 4 measurements, so not a terribly large amount, but they were all telling us the same thing. And that's that these galaxies are not like today's elliptical galaxies. They may have stopped forming stars, giving them their red appearance, but they don't have the same shape. Fundamentally, they're disks of stars. They're not round balls yet. And finding that these huge red galaxies are actually tiny, rapidly spinning disks of stars was really strange to me. It's kind of like discovering a transitional fossil because galaxies like that don't really exist anymore. So to put a bit of a biological analogy on it, we might think that seals evolved from a land-based ancestor, but when you actually find a fossil of a walking seal with feet, it's still strange and exciting, and it's really what you need to prove the case. So this discovery and a lot of others by astronomers around the world are leading us to rethink our history of how the biggest galaxies came to be. They might have been, as I said, the most boring galaxies that just formed quickly a few billion years after the Big Bang and then basically sat around doing nothing for the rest of the universe's history. That's what this little cartoon suggests. But now we think that these galaxies actually had a more complicated and interesting life, and they actually kind of emerged rather gradually. Now, I'll show you a little timeline outlining this new picture. The earliest parts are still, I think, the part we know the least about. In the first couple of billion years of the universe, we know these galaxies must have been just bursting with star formation. But then at some point, a few billion years after the Big Bang, for reasons that we still don't understand, and which are the focus of a lot of research, that star formation stopped. And what we've now learned is that the relic that is left behind isn't a fully formed elliptical galaxy. It's massive and it's red like an elliptical galaxy today, but it's small in size and seems to usually be a quickly spinning disk. And so for a galaxy like that to kind of undergo a metamorphosis into a giant elliptical galaxy, it has to change quite a lot. It has to become bigger in size and rounder in shape, and it has to stop spinning too. And we think that now that the way it does that is by merging with other galaxies. But it's a bit different than the dramatic collisions that you saw Hubble images from at the beginning of this talk. Those happen, but in addition, there's also a steady drip onto massive galaxies. We think that they're surrounded by a swarm of much smaller galaxies, basically, that are slowly falling into the bigger galaxy and being consumed by it. And that steady drip of small galaxies can fuel the growth of these galaxies and also cause them to become rounder and less spinning because that swarm is falling in from all directions. So it should make a symmetric galaxy in the end. And nothing is more symmetric than a giant elliptical galaxy like the images you saw at the beginning of this talk. So I said, we're always looking for the simplest explanation in science, but the simplest one that fits all the facts. And now that we've gotten a lot more observations, we're sort of forced to revise our picture of how these galaxies came to be. And it's more interesting, I think, than we thought. But there's still a lot that we don't know, especially that early period in the first couple of billion years. And one way to learn about that early time is to study the chemical composition of stars in these lens galaxies. That can tell us about what kinds of stars are formed over what time period. Marzi Jafarizani has been leading work on this. And for one of our lens galaxies, she's measured the amount of 8 different elements. And you can see them boxed on the periodic table here. And they might not look like much because the periodic table is a lot bigger. But if you think of the fact that before her work, there was only one galaxy in this period of the universe where even 2 elements had been measured, then you can really appreciate that her work was a big step. And she was our first UC Riverside Carnegie graduate fellow and just successfully defended her PhD thesis today. So Marzi's work, I think, is going to tell us a lot about these galaxies' distant past that we really couldn't learn in any other way. But we know that to make more progress, we're still going to need new instruments and new telescopes. So I'm very excited to be the co-project scientist for MIRMOS. This is the Magellan Infrared Multi-Object Spectrograph. It's an instrument that's being led by Nick Conaderas, one of my colleagues at Carnegie. And the team that you see pictured here, we're all working to keep the Magellan telescopes really at the forefront by designing this world-class infrared spectrograph. We're still raising money for it. We were excited recently to receive a grant from the Heising-Simons Foundation to support its development. And I'm really excited about MIRMOS for many things, but I think what makes it special is that it can excel at many different kinds of science. So it'll be spectacular for recording the light of many distant galaxies, like you've been seeing in today's talk, about 100 at once. But it can also do very different things. It'll be great for scanning the atmospheres of other worlds in our galaxy, for example. Later this year, in October, I'm eagerly awaiting the launch of the James Webb Space Telescope. This is NASA's next flagship mission. And what you see here is an animation of it deploying in orbit to form a telescope that's about as big as the Magellans, but about 1 million miles away. So it's an incredible technological achievement, and I have no doubt it will revolutionize our view of the universe in many areas. Astronomers have been really anticipating the Webb for decades. So I'm happy that one small part of what it's going to do in its first year is observations I proposed of this really special lensed Proto-Elliptical Galaxy that I showed you today. And with the Webb, we're going to get to look inside this galaxy, which is, again, 10 billion light years away, at a level of detail and sharpness that we really could never do, basically beyond our own cosmological backyard. And so I think that's really going to tell us a lot more about what was happening in some of the biggest galaxies in the first couple of billion years of the universe. Now, looking further into the decade, Carnegie is a founding partner of the Giant Magellan Telescope, or GMT. It's currently under construction at Las Campanas in Chile. And the GMT has many amazing capabilities. But I think perhaps one of its most amazing is its use of a technology that we call adaptive optics. This is the technology that essentially counteracts the blurring of galaxies and stars as their light passes through the Earth's atmosphere. And the GMT does this by launching this trio of lasers you see in this rendering that probe about 50 miles of atmosphere above the telescope. And what this allows the GMT to do is make images that are about 10 times sharper than even the Hubble Space Telescope, which basically means that for the GMT, we'll see every distant galaxy as sharply as we see these lens galaxies that we rely on today. And that's really exciting because it means that for the first time, we'll be able to look inside a lot of distant galaxies, going back close to the beginning of the universe with incredible sharpness. It's very exciting, but only one of the many amazing things that GMT is going to do. It'll revolutionize astronomy in many areas. So I hope you agree we have a lot to look forward to in the next decade. I'm very excited about it, and I look forward to returning to the Huntington and giving you a bit of an update about what we have learned. So thanks again for attending today.
All right. Thank you, Drew. That was a really great talk. As always, I always learn so much from the talks. It's always fun to hear about them. Even though I'm a professional astronomer, I always get to hear the newest and exciting things. We do have a bunch of questions. The first is there's a question here from Neil. Let's go with that one. Who wants to know, can an elliptical galaxy, you noted elliptical galaxies don't have rotation, that's pretty important to the definition here. Can an elliptical galaxy regain rotation? In other words, can it interact with a black hole or another galaxy? Can they regain that rotation?
Yes, that's a great question. So usually we think of transformation of galaxy shapes as kind of a one-way street where disk galaxies merge and become elliptical galaxies. But a galaxy that has become an elliptical, if it, for example, accretes a lot of gas from another galaxy that flies close to it or actually merges with it, can regrow a disk and become kind of a composite system. So galaxies actually can change shapes in both ways, and ellipticals can regrow disks.
Excellent. So the elliptical galaxies are the biggest galaxies we see in the local universe. There's a question about what are the smallest galaxies. So I'm wondering if you could give the full range in terms of sizes relative to the sun or something like that.
Sure, yeah, that's a great question. I think one of the most remarkable things about galaxies is the huge range of masses and sizes that they have. So I've been talking today about some of the most massive galaxies. The very most massive galaxies have a mass that is about, let's say, 1 trillion times the mass of the sun. And those galaxies sit at the centers of galaxy clusters that we talked about, and they get so huge because they're kind of like galactic garbage disposals. They're surrounded by these big galaxies that are pulled in by the gravity of the galaxy cluster and kind of coalesce into these monster giant galaxies. But at the other end of the spectrum, there are tiny galaxies near to our own Milky Way that have a mass less than 1 million times the mass of the sun. So that's a huge range, and those galaxies are mostly dark matter and might only be as bright as a few hundreds of suns. So there's an enormous range of galaxies, and I've only touched just a little bit on their true diversity today.
So related to dark matter, I'm wondering, we always get lots of dark matter questions. And I'm wondering if you could say something about lensing in terms of dark matter. Can you use lensing to find dark matter, is the question.
Yes, that is a great question. So one of the things that lensing is useful for, besides magnifying distant galaxies, which I emphasized today, is that it provides a way to measure the mass of the object that is doing the lensing. So I talk specifically about galaxy clusters acting as lenses. And in those instances, you can use observations of lensing to weigh the cluster, basically. And this is actually one of the pieces of evidence for the existence of dark matter, because lensing tells us that the amount of mass in these clusters exceeds the amount that we think is there in stars and gas by a very large factor. So lensing now is used not only to determine, for instance, that clusters are mostly dark matter, but to do much more detailed work and map out how the dark matter is distributed within galaxies and galaxy clusters. And that's important because we still don't know what the dark matter is, and we're trying to get at that and learning about more detailed picture of how it's distributed in galaxies can give us some clues about the nature of what we think is a new subatomic particle.
So, of course, the other interesting topic that we heard a lot about in Tom Holline's talk are black holes. And so there's a question, do these giant ellipticals have black holes, and why?
Yes.
The first part might be easy, the second one might be harder.
Yes.
Go ahead.
Yeah. Yes, so one of the interesting things about black holes is that they seem to know about the galaxy that they live in. So very massive galaxies, like the ones I've spent most of this talk focused on, have the most massive black holes that we know about, billions of solar masses. And they have the opportunity to grow because, in part for the same reason that these galaxies have grown. They the galaxies have a lot of mergers, or maybe they're in the center of a galaxy cluster, and they can accrete a lot of material from other galaxies that feed the growth of those black holes that we know lurk at their centers. How the black holes came to be in the first place, though, is a very active topic of research, because we can see black holes now in the first billion years that are already incredibly massive, and we really don't know how those came to be. One of the other really interesting things about the GMT is that it can take such sharp images that it will actually be able to measure masses of black holes to much greater distances much earlier in the universe than we have ever been able to do before. So I think we'll be able to have kind of a new census of black holes and how big they are and how they've grown over time in the next decade.
Great, okay, we'll do one more question and then we'll wrap up. So you've looked at these kind of proto-ellipticals, these things way back, right, that look kind of like ellipticals in some ways, but clearly not in all ways. Mm-hmm. And then we have ellipticals kind of in the local universe. So somewhere in between there, the ellipticals have to start really looking like ellipticals. And I'm just wondering how far out, do we know where that is yet, and how does one explore that?
That's a great question. We don't really know where that is yet, and that's because it's very hard to measure the motions of stars in galaxies, even ones that are quite a bit closer than the ones I've been talking about. So the latest measurements show us that about, let's say, 7 billion years ago or so, galaxies were still spinning more than they are today. So they hadn't yet fully become ellipticals, even, say, 5, 6, 7 billion years ago. But they were sort of on their way. They were less extreme than the galaxies I've been showing here. And so what we're working to do now is build up bigger samples, because once you start going 8, 9, 10 billion years ago, we can count on my 2 hands the number of measurements that we have. And so we really need to get a few more measurements and to be able to actually track out the history of how elliptical galaxies really emerged over time.
Great, excellent. So as always, the answer is more work and more observations,
yes.
more telescopes, more instruments, and more data.
Yep.
Well, thank you, Drew, for a really great talk, and thank you, everybody, for joining us for our series. Again, we look forward to seeing you, hopefully many of you in person, in the spring, which will be our 20th series in 2022. That's very exciting. Our 20th year of the series. We'll hopefully see many of you in the meantime at other events. And we thank you again for joining us. Thanks, Drew.